Hello, everyone. So this week is where we get to put into action all the work we've done over the past few weeks, learning, sort of building our organic chemistry tool chest so that we can start talking about functional groups and the type of reactions that those functional groups undergo. So this chapter is going to be all about our first functional group, which are alkyl halides. And we'll see the type of reactions that they undergo and all the different considerations. It's a particularly long chapter, so please make sure that you divvy out the right amount of time. So first, we're going to talk about the two main categories of reactions that this functional group undergoes, and those are called substitution and elimination reactions. So first of all, what are we talking about here? We're talking about alkyl halides. So just a quick example would be something like, right? We learned how to name alkyl halides, all that good stuff. The important feature of an alkyl halide, and in particular, like the ones that we're going to see reacting in this chapter, is that the halogen, in this case, halogens are often represented by X. You see it represents chlorine, bromine, or iodine. Notice that fluorine isn't on there. We'll talk about that in a second. But the important feature of all these alkyl halides that we will be talking about is that the halogen has to be bound to an sp3 hybridized carbon. Okay, this guy is called an aryl halide, not going to be in the same category. Notice that it's bound to an sp2 carbon, so we can pick that off right up the bat. This is a vinyl halide. Remember, we talked about those positions about a double bond. Again, you can tell it's not going to be in the same category because it's bound to an sp2 carbon. Importantly, though, it's not the benzene ring that disqualifies it. It is the hybridization on that carbon. So for example, if I had something like this would fall into this category. We will see reactions of these. This is what we would call benzylic. Likewise, if the halogen is located at the allylic position, so for example, something like this also is going to fall into the same category that we're talking about in this chapter. And again, the defining feature is that, these halogens are bound to sp3 hybridized carbons. That's what's really important. And again, there are two main types of reactions that these alkyl halides will undergo. The first one is a substitution reaction. Okay, so this is going to take place where you have an alkyl halide and a nucleophile. And what's going to happen is the nucleophile and the halogen are going to swap positions, right? So originally you have that nucleophile floating around in solution. At the end, you have the nucleophile bound to the alkyl group, whatever was on the other end of that halogen. Okay, so importantly, this carbon is the same as this carbon. You are just substituting what is bound to that carbon, substituting a halogen for whatever that nucleophile is. An elimination reaction is a little bit different. This is going to take place between an alkyl halide and a base. And what you're going to have is the elimination that is going to produce an alkene. So in this case, the base removes a hydrogen. That's what bases do, right? And you get an alkene. Importantly, let's just point out that the hydrogen that's being removed, let me use a different color actually. The hydrogen that's being removed is actually from one carbon over, right? So not that same carbon where the halogen was bound, it's being removed from its next door neighbor. That's where that hydrogen comes from. And so those electrons are going to come down and form a double bond or a pi bond, okay? Now, nucleophile, base, we use these two terms to describe molecules in terms of their behavior, right? Nucleophiles attack electrophiles, whereas bases accept electrons. But let's take a look at this compound right here. We've learned from our last chapter that this is both a base and a nucleophile. And so what we're going to see is that these alkyl halides, right? So for example, we have, this would be 2-chloropropane, will undergo both an elimination and a substitution reaction with this substrate. chapter is that these two reactions are competing with one another. And to be honest, we're going to first talk about substitution reactions and elimination reactions. And then at the very end, we're going to how do we figure out which one of these products is the major product, which one is the minor product. But just to give you guys a little bit of the punchline. The other thing I want to point out real quick is that you'll see these nucleophiles, kind of how it's written here, NaOH. But of course, the important player is actually the hydroxide ion. That's what's the nucleophile, right? Remember that sodium, as well as potassium, any of those first column elements there, they are very readily willing to give up their electrons. So when I want, and it's really sodium and potassium that you're going to see most often here. But what I want you to do when you see a sodium or potassium is immediately just think in your mind, replace it with a negative charge. Okay, because that's really the species that's going to be interesting in the chemical reaction. So then terminology real quick. In a reaction, you have a substrate. So that would be, your substrate's kind of the one that you care about. It's the organic molecule that you're transforming throughout your reaction. So in this case, this would be our substrate. The reagent is the thing doing that transformation, right? So reagent is in this case the hydroxide ion or sodium hydroxide. Both of these are your reactants, but you'll hear us refer specifically to the substrate, again, that organic, that alkyl halide in this particular case, and then the reagent, which you're adding in order to transform that substrate. So it's kind of just the roles that they're playing. And then of course the products is everything over here. Although you'll notice in organic chemistry, we get lazy and we often only write the products that we care about, right? Water and sodium chloride, they absolutely are going to be produced. In terms of having your balanced chemical equation, you would need to include them. In organic chemistry, we get lazy sometimes and we only really focus on the organic products. We leave off the other things. So it would not be unusual, even a little bit, to see this reaction written and just discard those two products altogether. They just wouldn't be written there. If you're writing a balanced chemical equation, it's important to include them. But in terms of your organic reaction mechanism, it's very often that they won't be included. So why alkyl halides? Why do they undergo substitution and elimination reactions? So two main features are really important when you're talking about alkyl halides. First of all is halogens are electron withdrawing groups, right? Somebody kind of shrewdly pointed out that bromine and iodine don't have all that much of a difference in electronegativity with carbon. Nonetheless, we think of all halogens as being electron withdrawing, okay? There's some weird factor that size plays. But there's going to be a lot more electron density here on the halogen portion of your alkyl halide, which leaves you with a deficit of electron density or a partial positive charge on the carbon. That makes that carbon a good electrophile, meaning that it can be susceptible to nucleophilic attack. Okay, so that's one main feature of alkyl halides that are going to be important. The other one is that the halogen itself is a good leaving group, right? Remember what did it mean to be a good leaving group? We had this very simple relationship before, which was good leaving groups are bad bases. Remember, we did this whole acid-base section, and we can tell that good or bad bases are the conjugate base of good acids, right? So if we look at our table over here, we have our strongest acid, and we have at the very tippy top there, all three of those are these, hydrochloric acid, hydrobromic acid, hydroiodic acids, all extremely strong acids, which means that their conjugate bases, the iodide, the bromide, and the chloride ion, are all very stable all by themselves. So by most stable base, we're really saying the worst base. And then likewise, things that won't be good leaving groups are things that are strong bases, right? So our cutoff that we have are kind of around here. So these are our best bases. Notice how fluorine doesn't make the cut, even though it's a halogen. So in this chapter, we're talking about alkyl halides. We're specifically going to leave off alkyl fluorides. They just don't behave the same. You see, I mean, it's not like a ridiculously bad acid, but it's just not going to be quite the same in terms of that good leaving group. So yeah, so everything that we're going to be doing in this chapter is going to be specific to iodo, bromo, and chloroalkanes. Okay. The last thing we need is just a little bit of terminology here in order to be able to like talk about what's going on here. So first of all, with regard to the actual alkyl halide itself, we have a sort of shorthand that we use to refer to the carbons in your alkyl halide. The carbon that is bound to the halogen is known as the alpha carbon. So substitution reactions will happen when a nucleophile attacks the alpha carbon. If it's one removed from the alpha carbon on either side, it's considered the beta carbon. And so in elimination reactions, the hydrogen is removed from the beta carbon. Okay, so this is just like some terminology that we're going to need. And then it keeps on going on, the gamma, everything like that, but honestly, those aren't going to be important. So really just being able to identify what the alpha carbon is and what the beta carbon is going to be really important. The other thing that's really important is that we have a specific way that we refer to alkyl halides with respect to the amount of branching that they have, okay? And I'm specifically talking about how many other carbons is the alpha carbon bound to. Remember, halogens can only ever have one bond. So a halogen can't be bound to 2 carbons or 3 carbons. But what about the alpha carbon? How many other carbons is that bound to? So if the alpha carbon is bound to 1 carbon, that's called a primary alkyl halide. If it's bound to 2 carbons, it's a secondary alkyl halide. And if it's bound to 3 carbons, it's a tertiary alkyl halide. I guess the other sort of extreme end of things would be, for example, this, and this is what we call a methyl. Where the alpha carbon isn't bound to any other carbons. Okay, but primary, secondary, tertiary, these are going to be important designations that we're going to use to refer to our alkyl halides. Okay.